in YouTube, and then as long as you're okay with it, then it'll be recorded, and most people actually watch it after the fact.
Okay.
Yeah. Mechanochemical reaction kinetics. Did I pronounce that right?
Yes.
Oh. So how long have you been at ODU?
I'm okay. I'm a research assistant professor, so I have two funded projects now. One has been to acquire a single crystal X-ray diffraction system, and I'm using it now with a high school student, and I will continue with undergraduates. And I also have a project funded by NSF to study to investigate and to measure for probably the first time the activation barriers of mechanochemical reactions and determine how they change with the different amounts of mechanical energy input to the reactants.
Great.
And I'm looking for a graduate student.
Sounds good. So how long have you been at ODU?
I live in Williamsburg. My husband is a professor of physics in the College of William and Mary, and so I am constrained to work in this region, and I have been in ODU since 2018, so since before the COVID lockdown, and yeah, so it has been good so far.
That's great. Nice.
You have been previously at Old Dominion University, right?
Yeah, I was there from 2017 till till December 2022. December. I was a postdoc there before I was faculty as well. So
I see.
I was a postdoc in 2015, I think, for a year. So yeah.
And which is your research field?
So I'm in physics, and I work in nuclear physics, and I'm a theorist. So
I see.
Just math. I'm useless in a lab. So I've learned that the hard way.
I see. But that doesn't have any correlation with the research that is done at JLab?
Yeah, it does. I'm actually physically in JLab right now. So my faculty. So I'm now a faculty at Berkeley in the West Coast, but my research is very much tied to JLab, and so
I see.
As soon as I finish teaching, I had to come here and work with folks, trying to finish my projects here. I still have students at ODU and postdoc in the area, so I figured it would be cheaper for me to fly here than for them bringing the whole team over. So
sure.
Yeah. So yeah, I'm very much tied to JLab. So so I see that people are starting to trickle in. Let's give them maybe like 3 more minutes, and then we'll go ahead and get started. We already got a question from the audience asking, how's our day doing? How's your day going, Selena?
So far it's good. Yeah. After this talk, I'm going to measure some single crystal diffraction data. I'm learning to use a new diffractometer. Yeah, so far it's going well.
That's
good summer.
Yeah. How about you? I think is Ali. Ali asked this question. How you doing, Ali, out there? Tell us where you are in the world. We want to hear from not just Ali, but everybody out there, that is joining the session. Tell us how you're doing. How's the weather? Hopefully staying I'm assuming that most people are having a hot summer, so hopefully you guys are staying hydrated and cool. But yeah, we want to hear from you guys. After all, we're all here for you guys, So they said that they're doing well. They're just busy today, as well as they got a lot of things going on. That's good. Well, we're glad that you're making time in your busy schedule to join us. And this is what I was mentioning to Silvina, that a lot of times folks are too busy to join in the live session, so they watch the recording after the fact. Actually, Silvina, have I been pronouncing your name correctly? Is it Silvina?
Silvina is okay.
And what about your last name?
Pagola.
Pagola. That one is easy. I mean, I don't know. Where are you from?
I am from Argentina. I did my I grew up there, and I moved to the United States for a postdoc first 3 years in 1998. I started. Then I returned to Argentina, and then for almost 2 years, and then I immigrated to Canada. I lived there for 4 years, and then I moved to the United States again since 2007.
I didn't know you were a fellow South American. Okay, sounds good. I'm from Venezuela, so yeah. Okay, good. So you guys must be. Were you guys proud of your soccer team last year?
Yeah, I don't really follow a lot the soccer or football team, but yeah, it's a big thing for Argentinians. Yeah, they take it very seriously.
Yeah, I mean, I was rooting for them. Yeah, I was actually physically moving from Virginia to California in the middle of the end of the World Cup. So like the story of how I ended up watching the final, I had to watch it on my phone in the middle of the road, and at some point, like, we didn't have connection, so I had to call my girlfriend, and I was like, can you hold the phone to the TV? And then she would be yelling, and I'd be like, what's happening? So anyways, so we have Jose Aquiles saying that they're doing well. They're reading a paper about the possible discovery of dark stars, and he's in the southeast of Brazil, so it's a little bit cold. All right. Okay, so I think we've had enough chit chat. I think we have a nice quorum here. More people, I'm sure, will join in. And what do we first take a couple seconds to introduce our speaker today, Dr. Silvina Pagola. It's a real pleasure to have her here. She's an ODURF, which stands for ODU, Old Dominion University Research Foundation. So she's an ODURF Research Assistant Professor, and she has an impressive background in chemistry and crystallography. And her research interest revolves around the kinetics of mechanochemical reactions, which is the topic of her talk. And this revolves around the synthesis of organic co-crystals and the advancement of direct space methods of molecular crystal structure determinations. If these words don't mean anything to you just yet, that's okay. I'm sure she's going to explain all these things. I'm going to be learning alongside with you, because I'm not an expert on this. Her great contributions have earned her several prestigious awards, including most recently the Most Inspiring Faculty Award from Old Dominion University in 2021. She's also a REYES mentor. I think she has 4 mentees, is that right?
2 right now.
2 mentees. All right, still, that's an impressive contribution. So we're remarkably grateful for her to be able to serve not just as a speaker, but also as a mentor. And we really are pleased that she's taking time out of her busy schedule, right? I mean, she's talking about doing research right after this. And also, she's in the market for a grad student. Okay, so if you want to impress her, and work with her. Just make sure you have really great questions, written down for the end of the talk. Feel free to put those in the Q&A chat. And so with that, we're very pleased that she's gonna share some of her expertise with us today. And we're just looking forward to gaining valuable insight from her impressive work. So thank you so much, Silvina. I'm gonna turn off my camera. The floor is yours, and thanks again.
Okay, so thank you for that generous introduction. And I will talk today, or the title of this talk is Mechanochemical Reaction Kinetics and Mechanisms. And as Raul said, I'm looking for a graduate student. So at the end of the talk, I will post my email. And please, if you're interested in a project like this that I'm going to speak about, just send me an email. Okay, so then what I'm going to talk about is I'm going to describe what is mechanochemistry, which are the advantages that mechanochemistry has in comparison with more traditional methods of synthesis from solutions. What are the instruments that we use in mechanochemistry, some history, and a particular synthetic method that is called liquid-assisted grinding. So I'm going to mention the research questions that I'm working on at the present, and some mechanochemical projects at Old Dominion University. And if you are interested in more information, I recently published this review in the journal Crystals that is open access, and it has more information about the current state of this field. So what is mechanochemistry? So certain chemical reactions occur at room temperature and ambient pressure without any occur like spontaneously, but not all. So in many cases, we have to add some type of energy to the reactants to induce chemical reactions. For example, if we heat them up, we have one branch of chemistry that is called thermochemistry, in which heat, induces chemical reactions. We also have, according to different types of energy, we have also photochemistry, in which the reactants are irradiated with ultraviolet or visible light, typically, and they produce reactions. And electrochemistry, in which the reactants are exposed to electrical potentials, for example, here in the electrochemical decomposition of water into hydrogen and oxygen. And in the case of mechanochemistry, which is a more recently defined branch of chemistry, reactions are induced by the application of mechanical energy. So what exactly this is? So it's energy that has been transferred to the reactants by the application of mechanical forces. Okay. And for example, in this case, we have the reactants, these yellow and white powders that we grind here with a pestle, and we see that the powders change color, and then the products have a different color, which is very often the indication that the chemical reaction has occurred. So IUPAC has recently defined mechanochemical reactions as those induced by the direct absorption of mechanical energy, so implying that there are mechanical forces that are applied to those reactants at the molecular or atomic level by the application of mechanical treatments. And for example, grinding is one of those. And the reactants can be in any state of matter, like solid, liquids, or gases. So then other mechanical treatments besides grinding is in the laboratory, typically ball milling, in which the reactants are placed in these reaction jars, which are shown here. In this case, they are made of acrylic. And inside them, the reactants are added, and they are mixed with some milling media. In this case, are steel balls, which are then colliding between each other and with the walls of the container. And in those collisions, they trap the reactants and they apply forces to them, and they transfer them part of the kinetic energy that they have, since there is a motor that is shaking these reaction jars in an oscillatory movement. In this case, it's a horizontal oscillation of the jars, but sometimes it's vertical oscillation. For example, we have here in this video from the Royal Society of Chemistry, we have an example of a mechanochemical reaction. So we have two powders there that are added into a steel reaction jar. One of them is blue, the other one is white. And here the milling media is that steel ball. And now those reaction jars are shaking in the and which a mechanochemical reaction could have been occurred. So one of the
Silvina, sorry
Yes.
to interrupt. You broke up for me for like a hot second. So I don't know if for others, but maybe do you want to say what you said a couple of minutes ago? So it was halfway through the video.
Oh, so should I show it again?
It's up to you. I think I got the gist of the video, but I missed some of the words you were saying.
Okay, so here is the reaction. So we have the two reactants. One is blue, the other one is white. There are two powders, and we load them in the steel reaction jar, and the jars are shaken by the ball mill. And as a result, there may have occurred a chemical reaction or mechanochemical reaction could occur. So these reactions are interesting. This type of chemistry is interesting because we don't really need reaction solvents. So, and if we use them, the quantities are very much reduced. And then these mechanochemical reactions are typically much more green than reactions that occur in solutions, since we don't need to purchase, we don't need to condition, and we don't need to dispose of the reaction solvents. So one of the 12 principles of green chemistry is to prevent waste. So this is very much the case, since we don't use solvents. We prevent waste, and these are typically greener processes than solution chemistry. So some history of these reactions. So we can see that mechanochemistry is actually known since ancient times by the Greek civilization, but has not been defined, or the term mechanochemistry invented until the late 1800s. So the first mechanochemical reaction described has been described by Theophrastus. Okay, that was the disciple of Aristotle, the Greek philosopher, and this reaction was the decomposition of cinnabar, which is this red pigment called vermilion, and it has been used by many civilizations along history, and it decomposes by grinding it in a copper mortar in the presence of vinegar into elemental mercury and copper sulfide. Okay, so this reaction was reported by Theophrastus in his book on stones, but then it was forgotten, since in the Middle Ages or after the Middle Ages, at the times of alchemy, the ideas of Aristotle prevailed. And Aristotle has said that no chemical reaction can occur in the absence of fluids. So then, even though alchemists have mortars and pestles, they did not consider really the chemical reactions that could occur by grinding solids. So it was more like reactions between liquids and elixirs that were studied at those times. So then it was the first mechanochemist has been Kari Lia, that was studying the chemical reactions of silver chloride and mercury chloride that occur differently if the reactants were heated up or if the reactants were ground in mortar. So, and the identification of a different branch of chemistry as mechanochemistry and the invention of that term was done by Oswald in the late 1800s, and then it was defined by Heinecke. And at present, we have a different branch of chemistry, and some people has called it chemistry 2.0 because it has many advantages in comparison with chemistry in solutions. So what instruments we use for mechanochemical reactions? So one of them is an agate mortar with pestle, as I said previously, in which we applied shear forces. Shear forces are the ones that produce surfaces sliding one with respect to each other, or non-hydrostatic compression forces in the reactants. So, and other instruments that are used in the laboratory for more systematic study, controlling the experimental variables that makes mechanochemical reactions to occur, are the ball mills, which can be of the planetary type, like this one, in which we have these reaction jars. And we have that there is a horizontal plate that rotates a certain frequency, and the reaction jars rotate in the opposite direction. And inside there are a milling media that is colliding and transferring energy to the reactants. And also we have the shaker type ball mills, like the ones that I showed before, with different types of reaction jars, in this case made of acrylic, or sometimes they can be made from steel or even other materials. So then while this milling media is shaking, then they maintain kinetic energy. So it's shaken by a motor, so they maintain kinetic energy, and they impacts they drop the reactants and they transfer them part of that energy, which produces mechanochemical reactions. Another reactions in another instrumentation for mechanochemistry are the twin extruders, in which they can be used for reactions, mechanochemical reactions that has to be scaled up. And they also can be carried out in continuous flow reactors. For example, the single or twin screws are in the barrel, which is this part. The reactants are inserted through the feed port, and the barrel can be kept at room temperature, or it can be heated up or cooled down. And after the mechanical treatment, the reactants are obtained, the products, sorry, are obtained in the exit port. So the materials, the products can be obtained in kilograms per hour quantities. And IUPAC has identified these reactions in twin extruders as one of the 10 potential new technologies that will make our planet more sustainable. So will produce more sustainable chemical reactions, potentially at the industrial scale. So all type of materials can be synthesized by mechanochemistry. So for example, we can have inorganic materials, metal organic materials, and organic materials. These is the symbol, that the ones that I'm highlighting there is the symbol for a mechanochemical reaction. And during the 20th century, a lot of these studies started with metal alloying. So to prepare alloys, which cannot be obtained by different synthetic methods that are applied in that field. So, but then more recently, so there are lots of materials that have been prepared by mechanochemistry, and they are simple oxides, nitrides, carbides, transition metal, ceramics. There are nanoparticles, there are even gases, for example, ammonia or syngas can be prepared by mechanochemistry. There are organic materials such as pharmaceuticals and other organic molecules in which the atoms are covalently bonded. We also have polymers, peptides, and reactions of biomass. We have metal organic frameworks with a myriad of applications and transition metal complexes. Essentially, all materials can be synthesized by mechanochemistry, all material types. So one recently developed mechanochemical synthetic method is liquid-assisted grinding, in which we grind or mill powders with small quantities of liquid additives. So those liquids are measured, the quantity of those liquids are measured as the volume of the liquid in microliters divided by the mass of the reactants in milligrams. And typically for liquid-assisted grinding, so this value, this parameter eta goes from 0, which is neat grinding, so no liquid added, to 2, and if it's done in a ball mill in a closed container. And then we form, if we add more liquid, we form pastes, and I tend to call these kneading, although the definitions is a little bit fuzzy. And then if we add sufficient volume of liquid, we have the same reactivity done in a solution. So in which case the quantity of products or the formation of products depends on the solubility of the reactants in the particular solvent that is being used. On the contrary, in liquid-assisted grinding, the mechanochemical reactivity and the products that are formed is not dependent. It's not dependent on the solubility of the reactants in the liquid. For that, we use the term liquid-assisted grinding, not solvent-assisted grinding, just to emphasize that solubility is not really necessary to observe a reaction. So the presence of these liquid additives produces, of course, an enhanced mass transfer and diffusion processes, and typically increases the rates of the mechanochemical reactions, so they occur faster, and increases the crystallinity of the mechanical products that have been obtained. For example, one of the reactions that I studied and published around 2014 has been the formation of a co-crystal or products, which are charge transfer complexes of an electron donor, theta fulvalene, and an electron acceptor, chloranil, And according to the liquid additive that is being used for the mechanochemical reactions, in this case was in a mortar and pestle by manual grinding, when one can obtain this green powder with a particular crystal structure and particular charge transferred between the electron donor and the electron acceptor. And we also obtain, using more the most polar solvents such as water and dimethyl sulfoxide, we obtain a fully ionic product, which is black, and it has a different crystal structure and is fully ionic. So the electron donor transfer, all molecules transfer one electron to the electron acceptor molecules, which are these chloranyl. So we can see that the particular liquids have certain effects on the mechanisms of this charge transfer, and then we obtain two different products. So they are called polymorphs because they are made of the same molecules, this electron donor and the electron acceptor, but they are packed in the crystal in different arrays, so they have different crystal structures. And in this particular case, they have different charge transfer between the electron donor and the electron acceptor. So why this happens is not totally understood. It depends on the particular chemical reaction that we are studying, but it's not totally well understood. So the liquid assisted grinding or the medium products are more crystalline, are very crystalline, and it was possible to solve the crystal and molecular structure of this black form, the ionic form, from the synchrotron powder X-ray diffraction pattern, and the fit is shown here. The experimental points are in red, and the calculated points with the atomic coordinates determined are shown in blue. Okay, and the difference is here at the bottom, so it's a very good fit, and that allow us to determine the shapes of those molecules and their interatomic their atomic distances and the type of intermolecular forces that they are acting between the molecules in the material. So a different example that I published in 2019 has been the reaction, a similar reaction, not with chloranil, but with chloranilic acid that has, instead of two chlorines there, it has two hydroxyl groups. And again, so using neat grinding or low polarity liquids, we obtain a neutral polymorph of the products, and using very polar liquids, and in this case also protic liquids such as alcohols, we obtain the fully ionic product of the mechanochemical reaction. So the products have been identified by X-ray powder diffraction, and also the crystal structure of the new polymorph, this neutral one, was also solved similarly from the powder diffraction data collected in a synchrotron. And also the position of the hydrogens were determined by neutron powder diffraction data collected at NIST. Okay, so then these liquids are added as to the reaction. They have certain role in the mechanism and in the formation of one product or the other, and but we don't fully understand those roles. So other characteristics of mechanochemical reactions that have been studied by many other scientists in this field are that the quantities of the mechanochemical products, keeping the temperature constant, depends with the amount of mechanical energy, depends on the mechanical treatment that has been applied to the reactants. Typically increasing the milling frequencies, in this case, for example, for this particular reaction, and in this case from 12 Hertz to more than around 21 Hertz, so that oscillation frequency increases the conversion fraction and the amount of product that has been obtained. And in general, it is observed that the rate constants, let's say the rates of those reactions, increase with the milling frequency increase. And but it's not, this is known, but the quantitative description of this, say how it happens in terms of formulas and equations, is not totally well understood either. So the mechanochemical reactivity not only depends on the amount of mechanical energy added, but it also depends on the temperature, because the chemical, the combination depends on the combination of mechanical and thermal energy or activation that is provided to those reactants during the experiment. For example, here we can see for this reaction shown here that the yield, percent yield, increases with the temperature from more or less 10% at 40 Celsius to more than 90% at 80 Celsius. So there is more product when we increase the temperature. So then actually mechanochemistry does not exclude thermochemistry. We can heat up the reactions, and that way we can provide even more energy to the reactants to produce chemical reactions. So then the current research questions that my group is investigating now is how we can describe better the effect of those liquid additives into the mechanochemical reactions to in order to produce different products. So which are, to do that, we need to think of a possible reaction mechanism for the mechanochemical reaction. So this is, we need to think in terms of what those molecules or those atoms are doing before the reaction and during a transition state, and how the reaction could occur at the molecular and atomic level. Okay, so and how those mechanisms, chemical mechanisms, will be different from those that happen in solutions or in gases. Okay, that has been traditionally more studied more frequently. So how the mechanochemical reactions depend on the temperature and how they depend on the mechanical energy input in terms of more quantitative